So in this section, which is the last section of this course, we will cover some extra topics such as transverse vibration, higher critical speeds, and whirling of shaft. So let's begin with today's lecture, that is transverse vibrations. Transverse vibrations. So the first case is simply supported, simply supported simply supported beam carrying the load W. So let me plot the schematic representation for this case. So this is the support 1, and it is subjected to some load W here. So when it is subjected to some load, uh, it will deflect at some point. So like that, it will go some deflection. So suppose from this point to this point, it is A, distance is A, and from this end to this end, the distance is B. So if you have studied the strength of materials, you should know what is the formula for this case for calculating the deflection. So the deflection is equal to WA square B square divided by 3 into E into I into L, which is equal to W by lambda, which is the K equivalent. So you should be wondering where this relation came from. So we know that the natural frequency is equal to under root of G by lambda, which is equal to under root K equivalent by M. So after simplifying, we are going to get this relation here. So we can write K equivalent is equal to, after solving this equation, K equivalent is equal to 48 EI divided by L cube. So this is the first case. Now moving to the second case. So let's move to the second case. So the second case is cantilever beam carrying load W at free end. So this is the schematic diagram for this case. So here W is equal to mg. Let me raise this thing first. Okay, so up to this point, and the length is L here, and after subjecting it to the same load, that is W, the deflection will be looking something like this. So this is the deflection, that is del. So you have to assume that for all cases, the beam is massless. The beam is massless. For previous case also, you should consider that beam is massless. So we know that omega n is equal to under root g by del is equal to under root k equivalent by m. So for this case, the deflection is calculated by the formula WL cube divided by 3EI, that is k equivalent is equal to W by lambda, which is equal to 3EI by L cube. So k equivalent for this case is equal to 3EI by L cube. Now moving to the third case, and this is the last topic for this lecture. So let me list this thing first. Okay. So the third case is about a fixed beam carrying load W. So the arrangement will look something like this. So this is the fixed beam, and there is some load W subjected to it, and after plotting, the deflection diagram will look something like this. So up to this point, the distance is A, and from this point to this point, the distance is B, and the deflection is del here. So for this case, the deflection is given by the formula WA cube B cube divided by 3EI L cube. So we know that K equivalent is equal to W by del. So for this case, the K equivalent is equal to 3EI L cube A cube B cube. So if A equal to B is equal to L by 2, so for this case, the del is equal to WL cube divided by 192 EI. So for this case, the K equivalent will be 192 EI divided by L cube. So this marks the end of this lecture. In the next lecture, we will learn about higher critical speeds. So for now, thank you.